Hello everybody and welcome to the RoboCup at Home League competition. First, let me provide you with a short introduction to this category. The application of robots in many fields has been extended rapidly in recent years. From industrial robots to space explorers, now we can find them performing home services. A service robot is a robot that can assist humans to perform common daily tasks in shared environments, such as houses, offices, or hospitals. To achieve this, a service robot must be capable of understanding spoken and visual commands in a natural way from humans, navigate in known and unknown environments while avoiding static and dynamic obstacles, recognize and manipulate objects, detect and identify people, among several other tasks that a person might request. The RoboCup at Home League aims at developing service and assistive robot technology with high relevance for future personal domestic applications, while the Domestic Standard Platform League has as main goal to assist humans in domestic environments. The Simulation Domestic Standard Platform League comes from the necessity to standardize and spread the research on domestic service robots, where a series of baselines can be tested in a standard benchmark. The Simulation League provides a first attempt towards this goal, and is the result of a whole year of continuous work to meet the challenges the current global situation arises. Therefore, and to conclude, let me to congratulate all the participating teams. It is for them and because of them that we all can gather together here. Without their hard work, support, and enthusiasm, we wouldn't be here. Thank you for accepting the challenge. You should consider your participation as a win, and what comes next will only help you to progress. Thank you all. Now I will present the latest research on service robots. I hope you enjoy learning from each other.
Over the years, Austinville at Home has made developments in knowledge representation and reasoning, perception, manipulation, and so on. Our research goal has been not only to solve the individual RoboCup at Home tasks, but to create integrated general purpose and portable robot systems. To that end, we have designed and deployed a unified robot architecture for both the HSR robot and our custom building-wide service robots called Beta Vibots. As you can see in the diagram, the top level of this architecture has state machines that go through the specific steps for various tasks, such as tidy up, go and get it, and carry my luggage, and it calls low-level executors as needed. An integrated task planner and reasoner is used for situations that require deliberative reasoning, like handling arbitrary instructions in GPSR. And I will tell you more about it in the next slide. For successful autonomy, service robots need to maintain an up-to-date knowledge of its environment, and our knowledge representation system has to integrate diverse sources of information. Finally, we have developed executors that allow both the state machines and the plans to control the robot, and you can check out this paper for more details. As I mentioned, we wanted to create a flexible knowledge representation system that integrates different sources of information and supports reasoning and planning. For semantic knowledge, we use the SQL database, and here we have a visualization of the representation. In this database, there are instances and concepts that have unique IDs, and we use attributes such as isPlaced to describe relations between these entities and store data such as the pose, width, and height of a table. In situations where we need to do task planning, the semantic knowledge is given to the task planner, which reasons about the preconditions and effects of actions. In particular, we have studied the problem of planning in the open world where the robot has not seen all the objects. For example, if a user requests an apple but the robot does not know the location of this apple, a traditional closed world task planner would fail. We introduced an algorithm in this ICAPS paper to plan with hypothetical information and enables the search behavior to look at every possible location for this apple. To automatically acquire knowledge in the world, our semantic perception system passively perceives and integrates labels and poses of the objects over time. The system includes an efficient storage and querying infrastructure for semantic labels called Object Cloud, and it is integrated with the knowledge base. Here is a simple demo showing that the object labels are generated passively as the robot is moving. Besides daily objects, we have also looked into using signs around the building to automatically annotate the robot's map. You can check out this paper for more information. Another interesting related research problem is how to efficiently sweep the environment for new information. To that end, we introduced a deep R learning algorithm for continuous area sweeping with the goal of maximizing detections per second. And that is the end of this presentation. We are happy to answer any questions, and we look forward to meeting you at RoboCup 2021.
Hello everyone, we are Hibikino Musashi at home. We will introduce our techniques for our object recognition system. We use YOLO for the image recognition system. We need to train YOLO with a large number of pictures. First, we create a 3D model of objects. We use a smartphone application capable of 3D scanning called Clone. By using Clone, we can easily and quickly create 3D models of an object by shooting it on a dedicated marker. We use a turntable to create a 3D model, however, in this method, the bottom surface of the object could not be shot immediately. Thus, we shoot two flipped upside-down object 3D models of the same object to make a complete 3D model. Then, we combine 3D models of the object to backgrounds. For the backgrounds of the training images, we shoot background images, for example, a table, shelf, and other items. To adapt to various lighting conditions, we apply the automatic color equation algorithm to the generated training images. To incorporate the object images into the background images, we define several object locations on the background images. By placing the object images on the defined object locations, the training images for YOLO are generated autonomously. By this method, we can generate 400,000 training images from 15 class objects and 306 background images, for example. Annotation data for the training images are generated autonomously because object labels and positions are known. The accuracy of the YOLO is high, however, sometimes the robot can fail to recognize objects. This is an example of a misrecognition. Since the appearance of a rabbit toy and hedgehog toy is similar, it is difficult to distinguish them by using only the image. We are developing a soft hand with tactile sensors for the robot to distinguish similar objects. This sensor is made of silicon rubber, liquid metal, and coils printed on a circuit board. When a force is applied to the sensor, the liquid metal in the sensor will flow, and the inductance of the coil will change. We can measure the hardness of an object by observing the change in the inductance of the coil. Since this sensor is soft, the shape of the hand is flexibly changed to fit an object. Moreover, the robot can avoid damaging objects. We process the information from the sensor by a neural network. We use reservoir computing, kinds of recurrent neural networks to process time series information. Compared to a general neural network, the training cost of reservoir computing is low. We also develop a dedicated chip for reservoir computing. The computation speed of the chip is quite fast, and this chip consumes quite low energy, so it is suitable for the processor of the robot. By combining YOLO and soft hand, the accuracy of image recognition can be improved. In addition to the image from the camera and hardness from the soft hand, various information such as the roughness of the surface, the weight of the object can also be utilized to recognize an object. This information also can be processed in the reservoir chip quickly with low energy. We have introduced our object recognition system, the quick dataset generation system for the YOLO, and a highly efficient analyzing system of the hardness of the object by a soft hand and reservoir computing. We continue to research on this approach to realize smart robot which can help our daily lives in our home.
What would you like to know about the weather in London?
What's the temperature?
For the last experiment. Now I will mimic your head movements with the robot's hand and mirror your facial emotion with my virtual person's face. The last topic is the weather in Tokyo, Japan. Are you ready?
Yes.
What can I tell you about the current weather in Tokyo?
What is the temperature?
Ready.
Hey Popeye, could you bring me a fruit?
Okay. I see a bunch of different fruit. What would you like me to bring?
Could you bring me an apple?
Okay, I will bring an apple. Here you go. Anything else I can help you with?
Hello dear RoboCup organizers and participants. In the following, Team Zaturo from the Institute for Artificial Intelligence at the University of Bremen will show you how we managed to extract and execute our HSR. We will do so by presenting the software components responsible for the tasks of planning, reasoning, perceiving, manipulating and navigating, and additionally show further footage. We'll start with CRAM, the Cognitive Robot Abstract Machine. CRAM is a software toolbox for the design, implementation, and the deployment of cognition-enabled autonomous robots performing everyday manipulation activities. This allows for lightweight reasoning mechanisms that can infer controlled decisions, which allows the plans to be more flexible and reliable. The symbolic expressions and the knowledge representation are grounded into the perception and actuation routines, and also into the essential data structures of the control program. CRAM thus makes the requirement to state the whole domain in an abstract knowledge base obsolete. NAROP is an open-source knowledge processing system designated for autonomous service robots. It represents the age's environment and belief state with axiomatizations using the web ontology language OWL. Recently, the Institute for Artificial Intelligence enhanced NAROP's functionality by developing SOMA, an ontological model that extends the agent's capability to perform everyday manipulation tasks. A key feature of this library consists of the fine-grained action representation. Since autonomous agents must often cope with shallow and symbolic instructions, they must be able to fill those informative gaps with detailed, grounded, and real-value information. In addition to that, NAROP provides a hybrid processing architecture where the components of the control program are reused in order to acquire experimental knowledge. Those resulting pieces of information can later on be used to find suitable exit parameterizations in the real world. RoboSherlock is an open-source framework for cognitive perception. It allows the creation of different perception pipelines to appropriately handle a wide range of scenarios. Internally, it is based on the Unstructured Information Management (UIM). The different computational units are implemented as annotators, which can be seen as experts for a given perception task. The results of those experiments are then combined to find the best solution. Annotators are currently implemented with the usage of OpenCV and PCL libraries. KISSCAT is a constraint-based motion control framework developed by the Institute for Artificial Intelligence and used for navigation and manipulation of the HSR. KISSCAT allows to formulate motion control problems according to constraints which the controller enforces during the motion. These problems include motion constraints such as keeping liquid container horizontal or basic grasp positions. KISSCAT plans full body motions that satisfy the ball description as best as possible. In the following footage, we will show how the HSR manages to perceive the surrounding and navigate through the environment. The agent observes the floor and any possible obstacles lying in the way. In case such an obstacle is detected, a collision is avoided by slowly navigating around it. Lastly, we demonstrate a simulation of our Zoturo system using the HSR. In this case, we will show how the software components of the Institute for Artificial Intelligence interact with each other during the cleanup plan. The agent enters the arena and makes notice of the existing surfaces. By navigating to the first surface, RoboSherlock perceives the existing objects. The observed object type is then validated against NOROP's vast ontology entries. From the determined object type, NOROP then infers how the object can be grasped and where the designated placing area is. The motion control framework KISSCAT can then slowly grasp the object from the surface and then navigate to the destination of the bucket. This is repeated with multiple objects on several surfaces. Thank you very much, and we are eager to compete with you.
Using a similar approach, we are able to open the drawers. Hand coordinates with respect of the transform of the drawer knob are used for little local adjustments when we are close enough. Classification was attempted using Darknet, however it was not able to deploy it in the server. We developed a synthetic dataset of the YCB object dataset in order to train YOLO. Here you can see how for each object a different camera angle and different background color was used in order to optimize image capture. This was done to use our own pipeline of YOLO training. Since we were not able to deploy YOLO in the server, we had to use classical computer vision techniques for segmentation, such as cam-ins. In this example, you can see how successful segmentation was done to later use point cloud information for objects pose. Principal components analysis is used to estimate object pose. Detected obstacles are mapped as collision objects, so the robot can plan through them without colliding. We also developed our own obstacle avoidance system using the map server. You can see here how we mapped the obstacles to the server, and then we can navigate. PCA information is used to obtain a good gripper pose. Some objects are just not graspable from any angle. We try to line up relative to the least important of the eigenvalues. Using a similar approach, we are able to open the drawers. Hand coordinates with respect of the transform of the drawer knob are used for little local adjustments when we are close enough.
Hi, my name is Rémi Fabre and I'm the team leader of CATI Robotics. I'm here to discuss the few improvements we've made since last time we met, and that was back in 2019. I'll focus this presentation on two aspects. The first one is that we made a new head for the robot, and the second one is that we made new fingers to improve the grasping capabilities. There are several reasons why we changed the head. First, the original head had a structural fault. The pitch articulation used to carry too much weight, so if you added a screen, for example, it would tend to overheat. Now the pitch articulation only carries the camera, right? And the yaw articulation can carry as much weight as we want. So we added a few things: a microphone, a local computational power, which is a fancy way of saying we added a Raspberry Pi with some custom things on it, and a tactile screen. Also, we added RGB LEDs, and this is probably the most important thing because these changes were mainly motivated by our will to improve the human to robot interfaces. Actually, this was going to be used in a paper that focused on improving how predictable the robot is for laymen. Unfortunately, COVID happened, and then any kind of experience with actual people just got postponed. So I don't have any research results to show you guys, but hopefully that will happen. Lastly, the mouth and eyebrows are mostly for fun, but it's interesting how easy it is to make it change the emotion by just tweaking a little bit, right? In this picture, he's clearly angry, and here he has a bit of a smug face, right? Maybe someday we could just motorize them and make a emotion-based task in RoboCup. I don't know. The second thing I wanted to discuss here is the grasping capabilities. So our first competition was in 2019, and back then our grasping looked like this. The fingers were just rigid and had no sensing, and we use mainly the force and torque sensor in the wrist to make things a little bit more robust. So what we did is that if the sensor felt that a force was abnormal, the arm would just let it go, right? Instead of forcing against it, we'll just let it go. So in a way that made our movements more robust, because if a human or a tolerable interface would happen, the arm will just adapt and then do it again. This was very useful when we were grasping big stuff like the garbage, right? But it wasn't enough when we tried to go for more complicated graspings. In some cases, you really need to know if you managed to grasp or not. In this case, it was also the bag was heavy enough that we could just take it up and make sure it weighted, right? But when we're trying to grasp small things, we need, one, to know if you grasped it, and two, maybe find a way of increasing the accuracy of the arm movement. So to do that, we made new fingers. So the first version of the fingers looked like this. The second version of the fingers looked like that. And the final version looked like this. So how does it work? We added force sensing inside the fingers, more like pressure sensing, but kind of the same. And this way we know if we have something inside the gripper, because you can't just rely on is it closed or not, because sometimes you will just pressure something that can be crushed, right? In this example, we show that we can grasp fragile items without breaking them. The other modification we made is that we added a suction cup to grasp items that are otherwise very difficult or almost impossible to grasp. For example, in the RoboCup at home, it would be a plate, and in this case, a sticker. Thank you for listening. Bye.
Hi, my name is Francisco. I'm going to present our team, the Gentlebots. This is a team composed by members from two universities, the University of Juan Carlos in Madrid and University of León, all of them in Spain. In the top right corner, you can see our GitHub page, where all the code that we have used in this competition is available. You can see there also the web page and our Twitter account. We have participated in RoboCup since 2005 with Ivo in the four-legged leagues. We started with Now in Suzhou in 2008, and we integrated in RoboCup at Home League in 2016 in Leipzig, and we are also participating in other leagues like the European Robotic League and the Cyrock. This is the general architecture of our solution. The main goal of our approach is using ROS2 for everything. So we have the Docker in the top part of this slide. You can see the official Docker provided by the league organization. We have also another Docker with custom bridges to bridge the topics from ROS to ROS2. It's bidirectional, and we need custom bridges because we need a special quality of service for some topics. In the bottom part, you see our solution. We are using some other packages. For example, for perception, we are using DOPE. DOPE perceive object in the space with using deep learning, with orientation and position using the deep image. We have ported this software to ROS2 a couple of weeks ago. We have also in this architecture, but we haven't used it. The dialog flow is for the dialog. We are not using for manipulation the move it for ROS2 because it's very premature, and we have some nodes to communicate with the move it inside the official Docker. We have another module for attention to focus the camera of the robot to scan and to track the objects, and we are using navigation too. Our cognitive architecture is using Plansys 2, that is the software for a PDDLA planning in ROS2, and we are using also behavior trees. This architecture in detail is shown in this slide. In the right part, you can see in yellow our ROS2 knowledge graph. We have a distributed graph available from all the part of our architecture, is synchronized, and in this graph we have the world model and all the perceptions and all the knowledge used in the behaviors. So the DOPE, the information produced by DOPE is integrated in this graph and can be used from the behaviors. We have some levels. In the bottom part, you see the mission control. This is a finite state machine with some state. In each state, you can set a goal for Plansys 2. The Plansys 2 calculates a plan to achieve that goal and activates, depending on the plan, activates the different actions. The actions are implemented as behavior trees. This behavior tree can access to the graph, and the leaves of this behavior has the functionality to communicate with navigation, manipulation, attention, or whatever. And in each behavior tree, using the port, you start. You get information. For example, there are nodes that get information for the graph and start the communication to the other nodes of the behavior tree. In the bottom part of this slide, you can also see the selected publication related to RoboCup at Home that we have produced since last RoboCup. All the publications are from the last couple of years, and you can see, for example, it's important. The Marathon 2 is in the IROS 2000. 2020 that was awarded with the RoboCup Best Paper Award. Thank you.
Welcome to Team Homer at Uni Koblenz poster session entry for this year's virtual RoboCup 2021 at Home tournament in the Open Platform League. My name is Daniel Müller and I'm the current team leader of Team Homer from the University of Koblenz-Landau in Germany. I will shortly describe the robot used by our team, which is Tiago, before I will present you the 4 main building blocks of our solutions for this competition. We take part in the Open Platform League using Power Robotics robot model for Tiago Steel Edition. Tiago comes with an integrated RGBD camera Astra Orbec with a resolution of 640 x 480 pixels for RGB images and point cloud data. The camera is mounted inside Tiago's head, which can be panned and tilted. Tiago Steel Edition comes with a 7 degrees of freedom arm with parallel gripper. In addition, Tiago's torso can be raised and lowered for reaching targets in a wider range of heights. Tiago's base also features differential drive and a Hokurio laser rangefinder with 5.6 meter measuring range. For mapping and navigation, we use our self-developed open-source ROS packages Homer Navigation and Homer Mapping, which are publicly available on GitHub. The mapping component uses a particle filter for localizing the robot and building up a 2D grid map of its surroundings using the current 2D laser scans. An additional map layer is formed and updated while driving by down-projecting the RGBD sensor's range measurements of the robot's current view. This enables avoiding small and hard-to-see objects while navigating through the arena. Our navigation then uses all map layers to perform a grid-based search for computing an obstacle-free path to a target location. For general object detection, known and unknown objects, we rely on a self-developed image-based clustering algorithm which is applied on the RGBD camera's range measurements. Pixel neighbors are evaluated based on similarity measures as, for example, their distance in space, or the deviation in their contained surface's normal direction in order to form clusters of support planes and objects positioned on them. With respect to the surface's orientation, 3-dimensional oriented object bounding boxes can be formed from these clusters by using principal component analysis. These fitted boxes are afterwards used for matching object detections from different points of views and times, and for estimating suitable gripping poses for grasping an object. For object recognition, we use YOLO version 3 and train it on generated synthetic data for use in the Gazebo simulation environment. We import the YCB model data to Blender and render images and arbitrary object poses to the camera. The underlying ground truth data for labeling the rendered images is hence automatically provided. Our synthesized data is furthermore augmented by adding random clutter background data in order to make recognition more robust for deployment in more complex scenes. Having identified an object to be manipulated, we compute best grasping poses for Tiago. Afterwards, finding a valid arm trajectory and executing it is done using MoveIt. We fill an octomap with the robot's range images for collision avoidance for moving the gripper towards a goal position near the object. Cartesian movement is then used to move into the object itself. After having successfully gripped an object, the bounding box is attached to the anti-effector in order to not to collide with anything else while moving the arm back. Thank you for your interest in our approaches and fingers crossed for having interesting and successful competition.
We are the Leeds Autonomous Service Robots team, or LASER, from the University of Leeds in the UK. We are a team composed almost entirely of undergraduate students, and this is our first RoboCup. In the last couple of years, we built the infrastructure from the ground up, and more recently we're focused on 2 themes that are going to describe here: human-robot interaction and robot manipulation. For human-robot interaction, we devised an anonymized feature vector that we use to recognize the same person between interactions with the robot. And we use it, for instance, for person follow to follow a person in a room with other people, or in leading someone to be able to let the robot turn around and recognize that the same person is still following the robot. We also used OpenPose to process the skeleton of the person for different tasks. For instance, I'm showing here recognizing that a person in a coffee shop is trying to get the attention of the robot by raising their hand or waving. And by looking at what the person is pointing to, because they may want to describe an object to the robot or tell the robot to pick it up. Here we are looking at exactly where the person is pointing to, and if there is more than one object in that area, the robot will ask questions to disambiguate. We also developed a navigation module that is object and human aware, in the sense that when there is an obstacle that is blocking the path and it is not possible for the robot to go around the obstacle, it'll see what kind of obstacle that is, if it is a person, a large object, or a small object, and depending on the categorization, a different handler will either ask the person to please step aside, or pick up a small object, or try to push aside a larger object. Then we have done work on manipulation. This is at the research level, and it's not integrated in the platform yet, but it's very relevant to RoboCup at home. So here we are trying to get the robot to move a particular object to a target location on a shelf. And we don't want to compute collision-free trajectories, as most methods do, but actually be able to exploit physical interactions with the objects, for instance, by pushing them aside. Now, this is very computationally expensive, and it's the reason why usually planners try to compute collision-free trajectories. But here we are using an abstract representation that you see in the top left corner that captures the important part of, the shape mostly of the objects on the shelf. And then a planner plans offline beforehand, creating a data set of plans that we use to distill them into a policy and value function. And then we further refine this policy and value function through reinforcement learning, and finally use it in a, try to restart the video, in a receding horizon planner, which then only has to plan for a few steps ahead, and is able to handle these physical contacts without having to run very expensive simulations online. The next work and last work I'm going to show you is in collaboration with the Department of Psychology. We have tried to devise a human-like motion planner. So we ran experiments with human subjects reaching for objects in a cluttered environment. We recorded their trajectories, and then we extracted a qualitative representation in terms of objects, gaps, and areas like forward or backward where objects have been pushed. And then, again, I'll try to restart. Videos here are very moody. Okay, and then we use this high-level qualitative representation to plan very quickly in a cluttered environment, which would otherwise require the planner to work for several minutes. And also we generate, as the title says, human-like plans, in the sense that they exploit the gaps and move the objects that a person would also do as per the trajectories that we have recorded. So we presented this at ICRA last year, and as I said, it's a collaboration between several people, both in the School of Computing and School of Psychology at University of Leeds. Okay, this is an overview of our research, and we'll be happy to discuss with you at the poster session.
Hello, we are the Leontech team. The Leontech team was founded in 2017 to address the scientific challenges of the RoboCup at home. The team is composed of students, engineers, and researchers from the University of Lyon, France, with different affiliations. We work on both Pepper Robot and Palbator Robot platform. But let's focus on the Palbator open platform. Palbator is made of a PMB2 PAL mobile base, enhanced with several hardware and software features. It contains a 7-degree of freedom arm designed to reach objects on the floor to the top of a shelf with a 1.5 kilogram payload. The picture on the left was taken in the Leipzig RoboCup at Home Arena in 2016. Since then, we added an human robot interface screen, a bottom 3D camera, Jetson Xavier, and we significantly optimized the hardware space. Our simulated version is an effort especially made for this RoboCup with a strong will to stay consistent in our development. Let's move on to the scientific contributions here on the right. Here is the word object management. During robot navigation operation, we scan the environment to add semantic information and object references. To do so, darknet's bounding boxes are combined with point clouds, bringing 3D information. A clustering operation using the time, distance, and object type drastically reduces the number of irrelevant entities. Finally, the resulting 3D entities are stored into a geographic information database. Overall, this allows us to easily interact with the environment. We already talked about the people features extraction and tracking, but let's take a glance on it again this year. We proposed a people management framework aggregating body and person features, including an original pose estimation using only a 2D camera. So we can keep track of people thanks to face, clothes, and we can know if the person is lying, sitting, standing, pointing something, what's their distance, and an approximating 3D location only thanks to the 2D camera. So we have a last part, the socially aware navigation among movable obstacles, social NAMO. Since RoboCup 2019, we improved our social aware NAMO approach for the problem of obstacle social placement choice. With only the static occupation grid, our social occupation cost grid characterizes the disturbance caused to human accessibility in all free space. Using this model in NAMO algorithm to direct their search results in placements that improve the overall space accessibility and organization over time. We implemented this new model in our open source ROS compatible simulator, and we are now working toward bringing social NAMO to multi-robot settings. You can find all of our contribution to the community here on the left, and you can find below our references. You can contact us through our website, email, or research team website. Thank you for your attention.
A very good evening.
My name is Melvin Ramon Leal Quiroz.
My name is Johan Lopez Castillo.
My name is Daniela Saray Cruz Hernandez.
We are students of the Technological University of the Southeast Veracruz, located in Mexico. We are studying the 6th semester mechatronic engineer in the automation area.
We are from the Mecha team. We are participating in the International RoboCup at Home 2021 tournament in the OPL League with our service robot Hoverbot. I would like to mention that it is the first time the university is participating in this tournament.
We are excited to have reached the final. A good teamwork was achieved. During our practice, we experienced voice recognition and spatial vision. We also use motor control to control our robotic arm. We wish to continue implementing this robot to activities within the school in a post-COVID context.
Greetings, everyone. I am Justina, member of the Team Pumas from the National Autonomous University of Mexico. I'm very happy to be here competing in this edition of the RoboCup. Now, a member of the team will present my technical specifications.
Justina is a service robot designed for operation in domestic environments. Its friendly and smart design allows
Greetings, everyone. I am Justina, member of the Team Pumas from the National Autonomous University of Mexico. I'm very happy to be here competing in this edition of the RoboCup. Now, a member of the team will present my technical specifications.
Justina is a service robot designed for operation in domestic environments. Its friendly and smart design allows the interaction with humans and their environment, while taking advantage of low-cost components available in the market. The main goal of the project is to encourage and promote science and engineering among students, giving them the opportunity to apply their knowledge in real-world application using high-end technology. Service robots are hardware and software systems that assist humans to perform daily tasks in complex environments. To achieve this, Justina has the following components: one mobile base using omnidirectional wheels, two anthropomorphic arms with 7 degrees of freedom, two speakers to generate synthetic speech, a Microsoft Kinect sensor as RGBT camera, one directional microphone, and an array of 4 microphones to detect sound sources. A laser allows Justina to create a map for navigation, and at last but not least, it has a system for image processing. Justina is based on the Birdbot architecture, and its operation is divided into several subsystems. Each of them has a specific functionality that contributes to the final operation of the robot. We use ROS as the main framework for interaction, where a module is represented by one or several ROS nodes. Besides, we use our own middleware called Blackboard to link all these nodes. When an order is recognized, the action planner defines a set of subsequent tasks to be completed using Clips as inference engine. And to check the process of the plant, a task accomplishment supervisor unit is used. The subsystem motion planner designs the movements plans and ensures that each step is properly executed. Justina uses the Microsoft speech recognition and natural language understanding to interpret the language. Besides, the conceptual dependency is used to find the structure and meaning of the sentence. And Justina uses YOLO for object recognition in real time. For face recognition, we use an artificial neural network called FaceNet, and TensorFlow for face, age, and gender recognition. Also, we use OpenPose for human key points detection. Our algorithm uses the point cloud to create a 3D skeleton, which is used as the input of a hidden Markov model to estimate the most probable gesture. To recognize an object, a raw color segmentation is performed, and a principal component analysis is implemented on each mask for category identification. This allows the calculation of the robot end effector angles for object manipulation. Besides, in our laboratory, we have the vision that in the future we will have a variety of robots performing a specific task, and we propose using Alexa to communicate with all these robots. The communication between Justina and Alexa consists of a local network where an Echo device is waiting for a user command. When a command is heard by the Echo, it is sent to Alexa voice service for recognition, and a request is sent to the local network. To attend the request generated by the ABS, a web service node is created detailing the command. Finally, a CD primitive is generated and sent to Justina for execution. To conclude, the team is still working to improve Justina capabilities, using the experience gained at each RoboCup since 2006. Also, we have promoted in our country the interest to participate in these competitions. Thank you for your attention and good luck to all.
A very good evening, I bid to the judges and other competitors all over the world which participated to the RoboCup at Home Virtual 2021 competition. Before I get started, let me introduce myself. My name is Siti Nurdina binti Nur Azmi, and I will be the representative from RoboCup UTHM team. Before I review our robot, let me give you some hint why we want to build this cleaning robot. Okay. Nowadays, as we can see, people are too busy focusing on their work, so they don't have time to do other chores when they reach home because they felt so tired and exhausted. With this problem, we decided to build cleaning robot which will take the trash on the floor. The objective of this cleaning robot, it will help to clean the house automatically when the instruction was given. So the first one is the autonomous navigation. Okay, this is one of the most important part in our robot, which we want our robot to move autonomously. Okay, as we can see here, this is the environment that we want, that we set up in gazebo simulation, and this is the map created to launch the autonomous navigation. Next, before we launch our autonomous navigation, we need to create our map first. So we use RP LiDAR A2 as our laser scan, which function 360-degree laser range, scanning the surrounding environment and generate the outline map. Okay. For the eyes, we need to use Kinect, which provide RGB camera, infrared projector, and detector. So when we give an instruction, the speech will convert to text. Next, the text will execute the Python file, and the robot will start to move autonomously. Okay, this is the result of the autonomous navigation. Okay, for the next part is object detection. You only look once real-time object detection in order to recognize the object inside the environment. For example, the bottles, the chair, or the boxes. Okay. As we can see here, the YOLO will detect the standing person as person. Okay. YOLO, they apply the model like person, like the bottles or the boxers or chairs to an image at multiple location and scale. This high scoring region of image are considered detection. It also predicts bounding boxes, which is this box, the yellow box, and the probability for each region. Okay, for the last part, the robot need to move its arm to collect the tin and throw it to the dustbin.
Everyone, my name is Lucas and I'm here to talk with you about HoboFay at Home and Era, our robot. Greetings everyone, my name is Lucas and I'm here to talk with you about HoboFay at Home and Era, our robot, which stands for Home Environment Robot Assistant. We are from Brazil, more specifically São Bernardo do Campo, São Paulo. And from here on out, I'll be talking to you a little bit more our structure and how we organize our robots. So for starters, the software that we are using is ROS Melodic Morenia and the Ubuntu 18.04, which both of them will be soon upgraded to ROS 2 and Ubuntu 20.04. For the processing part, we are using a Zotac ZBox EN1060K which has an Intel Core i5 paired with a GTX 1060 GPU. For the sensors, we are using the Microsoft Kinect V2 and the Action 3D sensor for our image feed and all of our vision system purposes, that being object detection and recognition. For our navigation, we are using the Hokuyu sensors, which are laser sensors placed both on the front and on the back of the robot. And speaking of navigation, our omnidirectional wheels are there to save us some time and give us some more maneuverability while in tight spaces. And also the manipulator, which has changed a little bit since the last competition, is now a 6DOF manipulator with 3D printed grippers. And finishing off, the head has an iPad 2, which is responsible for showing that face that you can see on the left picture. Two Rode mics for the audio inputs so that they can be captured, and the Matrix Creator board, which is a device that can locate where did the sounds came from, actually the inputs that we are giving it. So the improvements and upgrades that we have made on our robot, first of all, the manipulator is entirely new. It has a new gripper, as we've said before. The old gripper relied on the force that shaped the gripper to the object. This one doesn't, it hugs the object. Our vision system has been upgraded with the replacement of the old Kinect V1 to a Kinect V2, which can improve our image quality and give us more accurate results. And the virtualization process was very important due to the pandemics, and that we spent more time to give some attention to some areas that were needed and to make the model robot as precise and real to the world as possible. Our scientific contributions to the robotic societies are as follows. The first one is the social navigation, which is a better way for a robot to navigate. It's been being developed by one of our team members. It basically recognizes boundaries, social boundaries, while in a social environment, and tells the robot to step away from it so that it cannot go through it and ruin the moment. And the face mask recognition is something that we've seen to be proven very useful, since we are now obliged to use face masks for our safety and for COVID-19. So this recognition can judge if someone is or isn't wearing a mask, and by doing so, if the person isn't or is or not complying with the rules of the establishment that he or she may be in. Down below are all of our team members in the alphabetical orders. We thank you very much for your attention, and we are open to answer any doubts or questions that you may have. Thank you.
Hi, my name is Michael Denner, a team member of the German RT Lions RoboCup at Home team and research staff at the Department of Technique of the Reutlingen University. I would like to take 5 minutes to present our RoboCup at Home research poster. In the beginning, there are 5 departments at our RoboCup team. The navigation team is for moving the robot from one place to another. Second, the manipulation workers teach the picking and placing of all kinds of objects. Then there's the perception team that uses cameras, microphones and speakers to interact with the environment. All modules are connected by the people working on the brain. This abbreviation stands for the best Reutlinger artificial intelligence network ever built. Finally, the assembly operators invent new hardware and maintain our robots. Let's start with our research in navigation. For collision and obstacle avoidance, as well as trajectory planning, robots usually generate and use a simple 2D coast map without any semantic information about the detected obstacles. Thus, a robot's path planning will simply adhere to an arbitrary large safety margin around obstacles. A more optimal approach is to adjust this safety distance according to the class of an obstacle. For class prediction, we trained an image processing convolutional neural network. One of the main problems in the development and training of any neural network is the creation of a training dataset. We used methods and free open source software allowing a fast generation of annotated datasets. Our pipeline can be then applied to various objects and environment settings and is extremely easy to use to anyone for synthesizing training data from 3D source data. We created a fully synthetic industrial environment dataset with 10,000 of physically based rendered images and annotations. Subsequently, we trained a CNN with our dataset for coast map safety class prediction. We analyzed different class combinations and showed transfer learning the safety classes end-to-end directly with a small dataset instead of using a class lookup table that improved the quantity and precision of the predictions. We proposed 3 different class groupings on our dataset for our experiments. First, all dataset objects as their individual class. Second, similar objects grouped by type classes. And third, objects directly grouped into safety classes. The manipulation team works on a novelty for picking up objects. We generate volumetric 3D environment models with Octomap. The error in range measurement is usually very high and therefore an updated environment mapping in real time is necessary. Octomap is an integrated framework based on octrees for the representation of 3-dimensional environments. We use this new method not only for navigation but also for gripping tasks. Hence, this also supports the gripping point detection and orientation of the objects. In parallel, the team had also to handle the simulation challenges of picking a virtual object with a home service robot. Many experiments and trials took a lot of time, and finally there have been more and more successes. The perception team worked on synthesizing training images in Blender. The semi-automatic script is able to generate thousands of RGB images in a few hours. The objects are then extracted and combined with an artificial background that corresponds to the simulation arena. In this step, the labels and positions of the objects are also stored. In a second approach, an arena scenery has been built in Unity 3D, including random YCB objects in the shelf, on the table or on the floor. Again, the labels are also generated by Unity. Therefore, no manual annotation had to be done for this year's challenge. The training data then was trained on the darknet YOLO network and we achieved a high recognition rate. Our brain combines all modules and orchestrates all states of each challenge. The tool we used is called RoboCup, that supports the creation of state machines for robot programs. The specialty of RoboCup is the graphical interface, the hierarchies of state machines, and the integration of internal and external Python code. The communication of the modules was done by ROS topics and messages, and this is also controlled by RoboCup. Additionally, the brain is in control of the Docker containers and the application inside the containers. Last but not least, the hardware team worked on a bionic gripper with slip and grasping detection. Together with Festo, we built a soft bionic 2-finger gripper with force sensors on the inside. Thank you very much for your attention.
Hi everybody, welcome to the poster session presentation from the series Cybernetics Corporation from Germany. Hi everybody, welcome to the poster session presentation from the series Cybernetics Corporation from Germany. These are all our robots that we would have loved to bring to the competition, but I guess you all know the story and that's why we move on to the content right now. So, this is one thing I want to talk about tonight. This is the learning from demonstration, which we have been working on over a decade now. And it's a simple thing. You want to teach the robot a new ability that it has not yet, and you don't have any clue about programming. So what you can do is you can show the robot how to do something. And if you would, we take this pouring task here as a simple example. If you would just demonstrate that once, the robot would just simply learn it like a teach-in thing from an industrial robot and wouldn't understand anything about the task. So what we have to do is we have to do more than one demonstration with shifting the positions of all the objects involved. And what results then is if we look at, for instance, some trajectories corresponding the end effector distance to some involved objects, you see that there are parts in the demonstrations that have a very small and low and high variance. And the low variance parts is what we consider a constraint, and this is something that is relevant for re-executing the task and can then be used to form a generalized trajectory that is able to reproduce the task even in situations where the objects are totally differently placed as they were before. Again, without programming one single line. Now, the classic approaches here use the joint space. So you just record all the robot's joints, and then you can reproduce that stuff, and you can also like form generalized trajectories without the need of an inverse kinematics planner. What we're doing now is, what we have done is we have transformed this into the task space. So we only need a 6-dimensional vector and the gripper state in order to do a demonstration. This enables us to use hand tracking frameworks and other stuff to do the demonstrations. The result is the same. So we are still having these generalized trajectories, but now we only have the anti-vector positions, which enables us to use planners in between and also makes the whole demonstration part way more robot independent, because before it was really stuck to this one robot model. Now we can transfer the knowledge from one robot to another. And the next step here, which we are also working on at the moment, is to transform that into a higher level reasoning, so calling high level learning from demonstration, which starts to understand or starts to address the simple grounding problems when you're doing demonstrations like that, to enable the robot to understand what it's actually doing. Next part is something that we call situation awareness. This is dependent on a graph database world model. I'm not going to go into deep details here. I think most of you will know what this stuff is about. And what are we applying it to at the moment? So we are using this first of all to learn user habits. So each of you has its own way to organize your home. And this is what we are particularly interested in. So the robot observes how your home is organized over a longer period of time, and then forms spatial and temporal clusters with respect to everything that is there in a situation. So if, for instance, the Pringles can would be standing on your desk at 7 p.m. and there is an open beer bottle next to it, that might be something that some of you would consider as okay, and some of you would say, no, 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 this has to be moved away. And these are the things that we are storing and learning, and with this high-dimensional clustering, we are able to predict if a situation, given the circumstances, is okay or not. Another thing where we have applied this is when we are learning concepts. So in this case, this is referring to a tabletop setup experiment. So we're setting a table for a dining as exercise. This is, by the way, something that we would also show in the open challenge. And the idea here is also pretty simple. The robot is presented various scenes that are labeled okay and not okay. And with that, we are training a Gaussian mixture model in order to generate actions. First of all, classify if the scene is okay or not, and also to get as action pairs out of it, what would be the corresponding set of actions in order to transform this scene back into a normal state where it would be okay. Good. These are 30 seconds left, but in this case I would call it even, and take care, stay healthy, and bye bye.
Hello, we are the Lyontech team from France. Our team was founded in 2017 to address the scientific challenges of the RoboCup at home. The team is composed of students, engineers and researchers from the University of Lyon. We work on both Pepper and Palbato robot platforms, on navigation, perception and mapping of complex environments, as well as human-robot interaction. Our approach is built on recent methodologies linked to social navigation and deep learning. We developed an architecture dedicated to the orchestration of high-level abilities of a humanoid robot, which rely on several abilities such as those required in the RoboCup at home competition. The validation of our approach is based on many experiments performed in an apartment-like environment and in presence of several humans. Our architecture is described on the left. Basically, the main functional blocks such as robot navigation, object detection, people detection, now-correlated functions, and world mapping are all linked together through the ROS middleware, and they are orchestrated with a general behavior manager that manages scenarios. As for our scientific contributions, we have made advancements in world objects management. During robot navigation operation, we scan the environment to add semantic information and object references. To do so, darknet's bounding boxes are combined with point clouds, bringing 3D information in. A clustering operation using the time, distance, and object type drastically reduces the number of irrelevant entities. Finally, the resulting 3D entities are stored into a geographic information database. Overall, this allows us to easily interact with the environment. In 2019, we proposed a people management framework aggregating body and person features, including an original pose estimation using only a 2D camera. At this time, people pose and posture, clothing colors, face recognition are combined with tracking and re-identification abilities. The figure below presents the different framework blocks. First of all, the robot gets the scene information through the camera. This image is then processed in order to extract each person in the scene. Semantic informations are added concerning people posture, hand posture, and estimated position, like sitting, lying, standing, or pointing. Cues such as face and clothes are used to identify a person, face detection, color detection, and naming. Finally, all the semantic information is gathered and sent to the robot decision process. The robot can identify people, understand intentions, and has an overview of the scene. We have continued our work on socially aware navigation among movable obstacles, or NAMO. Since RoboCup 2019, we improved our socially aware NAMO approach for the problem of obstacle social placement choice. With only the static occupation grid, our social occupation cost grid characterizes the disturbance caused to human accessibility in all free space. Using this model in NAMO algorithms guides the search to placements that improve the overall space accessibility and organization over time. We implemented this new model in our open-source ROS-compatible simulator. We are now working towards bringing SNAMO to multi-robot settings. All the code and data behind these scientific contributions have been made available open source to the community as is shown on the left. Please do visit our website robocup-lyontech.github.io for more information or contact rafael.leber@cpe.fr. Thank you for your attention.
Hello, my name is Rui Betancourt and I am a part of Robot Home team from Instituto Superior Técnico Portugal. The rest of the team can be seen in the bottom of the slide. We are formed by PhD students, master students, and supervised by faculty members. Our aim is to implement our research in real robots and compete in robotic competitions so we can showcase our research in a fun and competitive way. We usually use this robot on the right called Monarch robot, but for RoboCup simulation, we will use Tiago Steele from Paul Robotics. Our functional architecture can be seen here. We will only be using the bottom since we don't need human interaction. We basically use object perception, navigation, and manipulation to complete our goals, combined with task planning. Our object perception is based on Darknet YOLO. We have two detectors working. We have a generic detector that detects more generic objects we usually see in our environment, like people, chairs, or tables. The specific detector is used depending on the competition. Every competition has a specific data set of objects we need to recognize, and so we train this specific detector for each competition. The detection from YOLO and the information from the depth camera is then used to determine an estimation of the pose of the objects, which is then fed to an extended Kalman filter that outputs the actual pose estimate of the objects throughout time. For navigation, we represent the world through a map that we generate by using FastSlam 2. This map is then used also for localization as well as the laser scanner and the odometry by using AMCL algorithm configured to our robots. Then for the navigation planning, we either use the navigation stacks planners like DWA and Dijkstra algorithm, or we use the navigation stack created by a researcher here in ISR that has two modes of navigation, a waypoint navigation based in fast marching method, or a navigation that follows a dynamic goal using a variation of dynamic window approach. For manipulation and grasping, we first obtain the objects from the world through the object perception. Then, according to the object that we want to grab, we first need to determine the grasp pose. We have also research in these fields to grab objects that we do not know a priori. So we try to grab objects, unknown objects, calculating these grasp pose through the point cloud. Then we also have interesting research in using the body as an extra degree of freedom so that the robot is not static while he tries to grab an object and uses its mobile base as an extra degree of freedom. Then, of course, we also use move-it inverse kinematics, and we use visual observing to correct any errors in the object perception or in the arm itself. To generate the tasks, to complete these more elaborate tasks, we need some task coordination. We divide these in these three layers: basic actions that are like rotate the head, perceive this frame, move to this location, simple actions such as these that are then used to create states that are more complex, such as navigate from this point to this point, or perceive this whole scene, or grab this object, place this object, states that are more complex and that are used then to build our state machine. That according with the states and the state transitions, we build a state machine that can accomplish these more elaborate tasks. We can see two of them here on these two videos. One is people following, the other is just grabbing objects, which is not as easy as it looks. In this RoboCup, we will be performing two tasks: clean up and go and get it, where we will be using states that are based in navigation, perception, and manipulation. Thank you.
We want to present recent research of a laboratory consisting in a telepresence robot focused on providing mental health care for COVID-19 patients, named Voodoo. The development of the robot took a four-stage approach. A first step of design was taken in order to address the requirements of the healthy. This work was done in a period of 4 weeks, thanks to the previous experience of the team in RoboCup at home competitions. A first visit to the hospital with the working prototype was carried out. During this visit, how the robot interacts with the hospital's infrastructure was analyzed. In addition, the hospital Department of Healthcare and Associated Infections analyzed the robot and defined the requirements for its future operation in the hospital. During following visits, the robot was operated by a psychointensivist and it interacted with patients. This experience was very successful, but other two requirements arose: the need for controlling the tilt angle of the camera for proper interaction with patients lying or sitting in the different positions, and the need for having microphones with noise cancellation to filter the noise generated by equipment used in the ICU. A final validation was carried out in a third visit. During this visit, the robot was inspected, and we got the final approval from both the HAI department and the ethics committee for using the robot inside the hospital. The main design requirements for the robot were simplicity, high usability, and easy operation by healthcare workers, and the possibility of being operated, handled, and transported by a single person. Moreover, the robot needed to be designed, developed, and built at a low cost, in a development time frame of just a few weeks. In addition, by considering the impossibility of having in advance neither accurate maps of the hospital where the robot would operate, nor the accurate location of the patient beds, the alternative of having autonomous operation was discarded, and it was decided to design a robot that operates in an assistive teleoperation mode, based on off-the-shelf devices. Also, open source software and the ROS framework was used in order to speed up the development. Here we can see the latest version of the robot with an updated position of the depth camera for better detection of obstacles in the hospital environment and improved audio output, this to overcome the ambient noise present in the hospital. In the two other photos, we show the proof of concept of the robot, analyzing the maneuverability around the hospital, like elevators, and long hauls to check the range. The robot was designed, built, tested, and deployed in just 8 weeks, mostly during an intensive quarantine in the city of Santiago. The three key aspects of this achievement are: 1. An interdisciplinary team composed of neurologists, psychointensivists, engineers, and designers who knew the specific needs to be filled and had a technical means to fill them. 2. The high commitment of the development team composed of students. And 3. The use of off-the-shelf devices and ROS packages which allow fast implementation of the robots. Two Voodoo's robots are used in 2 Chilean hospitals in order to regulate their use for providing mental and emotional health care to patients in the ICU. Thank you.
Thank you for watching, everybody. This was the end of this session, and we invite you to continue watching the next competition days, where we can see all these different approaches competing towards the same goal. So we invite you to keep an eye in this channel, and see you next time.